Hey, good afternoon, everyone. My name is Greg Johnson with Flowtech International. I'm here with Max Marian, who will be speaking to us today, actually on a pre-recorded session about machine learning in tribology. Max's full bio can be seen on the landing page of LRVS, so please go and check that out. I'm going to jump. I'll let Max say hi, but I'll
Hi, everyone.
queue up the video right now. Thanks, Max. Hey, also one last thing. There's a chat function on the right-hand column of your screen. If you have questions during the presentation, please put them in, and then should have about 5 to 10 minutes at the end of the session to answer any questions you might have. Enjoy the presentation.
Hello everyone, and thank you for switching on this presentation on machine learning in tribology. My name is Max Marian and I'm an assistant professor at Pontificia Universidad Católica de Chile. In the following, I will briefly introduce you to some core concepts of tribology, as well as some current trends and applications of machine learning in the domain of tribology. I will introduce you to an ontology database which could form the base for machine learning in the domain of tribology, as well as to a semantic annotation pipeline that can automatically feed the database. I will close my talk with a short summary.
So let's start with the basics. I will try to keep it short, as surely most of you are pretty familiar with it. Basically, a tribal system can be described by its system structure, input and output variables, and a functional conversion within the open or closed system boundary. The system structure consists of the relatively moving body and counterbody, which are rubbing against each other and may be completely or partially separated by an intermediate medium. Operational input variables such as load, kinematics, duration, and temperatures can be summarized in a stress collective. Depending on the latter, as well as any disturbance variables and the system structure, the body and counterbody physically and chemically interact at temporally or spatially varying locations. On the one hand, this results in loss variables such as friction and wear, which cause changes in the surface, loss of material, and energy dissipation. On the other hand, this results in the actual functional variables of the tribal system. The mechanisms and applications of tribology extend over several size scales. This ranges from processes on the nano or micro level in the field of physics, chemistry, and material science, such as the formation of boundary layers or shearing of nanoparticle layers, and ends up with machine elements and assemblies, as well as multiple tribological contacts in engineering sciences in the micrometer or the meter range, for example in rolling bearings or gears. Accordingly, tribometry, the tribological measuring and testing technology, covers all dimensional ranges of tribology, determining friction and wear parameters of tribal systems. The significance of various quantifiable measured variables usually depends on the underlying mechanisms, the measurement method, and the objective of the study. Given the function and structure of tribal systems, tribological testing can be divided into 6 categories according to the simplification of the system structure and the stress collective, as well as the environmental conditions. So this goes from very complex machinery field tests to rather simplified model tests with the well-known pin-on-disk or ball-on-disk setup. Thereby, profound databases in combination with machine learning and artificial intelligence approaches can support through the complexity of patterns and identifying trends within the multiple interacting features and processes. ML is part of AI and thus originally a subdomain of computer science. AI and ML are formed by logic, probability theory, algorithm theory, and computing. In a first step, ML involves designing computing systems for a special task that can learn from training data over time and develop and refine experience-based models that predict outcomes. The system can thus be used to answer questions in any given field. There are a number of different algorithms that can be used for ML, whereby the suitability is strongly task-dependent. Basically, algorithms can be classified as supervised learning or unsupervised learning. For the former, algorithms learn a relation from a given set of input and output data vectors. During learning, a teacher provides the correct inputs and outputs. In unsupervised learning, the algorithm generates a statistical model that describes a given dataset without the model being evaluated by a teacher. Furthermore, reinforcement learning features different characteristics, although it is sometimes classified as supervised learning. Instead of induction from pre-classified examples, an agent experiments with the system and the system responds to the experiments with reward or punishment. The agent thus optimizes the behavior with the goal of maximizing reward and minimizing punishment. While the classification of the 3 learning types mentioned above is common and widely accepted, there is no consensus on which algorithm should be classified to which category. But still we can see manifold different approaches ranging from support vector machines, decision trees, genetic algorithms, neural networks, and so on. Various ML approaches have also found a way into tribology, and over the years more and more have been employed to monitoring and controlling, analyzing, designing or optimizing tribal systems in many fields of tribology, from composite materials and drive technology to manufacturing, surface engineering and lubricants at different scales using experimental, literature or numerical databases. In the following I will show you some successful use cases. The first example is for training machine learning algorithms based upon a numerical database to predict the behavior of so-called elastohydrodynamically lubricated contacts, which we can find in concentrated rolling sliding contacts of machine elements such as gears or rolling bearings, where the components elastic deformation and the lubricant's hydrodynamics are superimposed. Thereby, we were able to demonstrate that using geometry, material and lubricant input parameters, ML approaches such as artificial neural networks that we can see in the center of the slide can predict relevant film thickness parameters more efficiently compared to more sophisticated simulation models solving physical equations and with higher accuracy and flexibility than analytically solvable regression equations, which are typically employed in higher level multi-body dynamics and system simulations. Thereby, we could show that in addition to integral parameters such as the minimum or the central film thickness, it was possible to predict the locally resolved film thickness values over the contact domain 20 times faster than the corresponding more sophisticated EHL simulations. We assume that this will boost the use of ML approaches to predict EHL parameters and traction losses in multi-body system dynamic simulations. Speaking about dynamic simulations, Schwartz and co-workers utilized ML regression methods trained by multi-body simulations to predict the dynamic behavior of various cages and angular contact ball bearings, and they reported that the regression algorithms predicted the highly nonlinear interplay of operational conditions and cage geometry with satisfactory accuracy. And the authors emphasized that the ML approaches will allow to analyze a new dataset in the shortest time without the need to perform new dynamic simulations. A more recent approach for monitoring and classifying the multivariant wear behavior of lubricated journal bearings was presented by Koenig and co-workers. As illustrated on this slide, an autoencoder was used for anomaly detection. Moreover, acoustic emission signals with a continuous wavelet transformation were utilized to train a convolutional neural network to classify the modes of running in, insufficient lubrication and particle contamination of the oil. Another example is from Sauer and co-workers who compared various supervised ML approaches for predicting the elastic and hardness characteristics of diamond-like carbon coatings on polymeric medical materials independently of PVD sputter process parameters. It was reported that Gaussian process regression featured highest accuracy compared to polynomial regression, support vector machines or neural networks. And slicing-based data visualization and process maps can further provide support to experts when designing coating systems and processes. One last example I would like to show you is from Egala and co-workers who studied epoxy composite materials with newly developed natural short castor oil fibers as unidirectional reinforcement of different length. The database was acquired from experiments utilizing flat pin-on-disc tribometer. And besides fiber length, the normal force and the sliding distance were varied, and the influence on the gravimetric wear, interfacial heat and friction were studied. Thereby, the relationship between variation parameters and target values were expressed by hidden layer artificial neural networks. And to find the best prediction, 73 different ANNs with varying number of hidden layers, number of neurons and different transfer function were tested stepwise. Thus, ML models with high accuracy were obtained, which, for example, ultimately allowed to optimize the material composition. So this was intended to give you just a very quick and shallow overview of what ML might be capable of when employed in various areas of tribology or lubrication science. If I sparked some interest, please be referred to very recently published article collection as well as a recent review article on the current trends and applications of machine learning in tribology. At the root of all advances made so far are multitudes of precise experiments across different scales and multiple physical disciplines. Based upon this sound and data-rich foundation, advanced data handling and analysis learning methods can be developed and employed to expand existing knowledge. The reuse of existing tribological knowledge, however, highly depends on the access to it and the quality of documentation. Producing experimental knowledge is usually divided into 3 steps of experimental design, experimental procedure, and experimental results, and involves a lot of background knowledge from the domain experts. First, the domain expert has to design an experimental setup, including the fabrication of the samples suited for the SS tribal system, the definition of target variables, the kinematical and operational parameters. The tribal system is the experimental model used for studying time-dependent friction and wear parameters and consists of at least 2 relatively moving objects in contact, an interfacial medium and environmental medium. The second step, the experimental procedure, is frequently carried out by standardized testing devices, producing measurement series as output files. Since tribological conclusions are based on the comparison of experimental results with those of a reference system, the experimental procedure involves different measurement series with a variation of the target variables. The last step, experimental results, is reached by analysis of the measurement series, an interpretation of the results, and a documentation executed by the domain expert. The knowledge gained from the conducted experiments is also the input for a new experimental design. Since there exists no formalization of experimental knowledge in the domain of tribology, this process involves a lot of manual work for the domain expert. Currently, no routine or schema for a formal and explicit documentation of the outcome from the experimental design step exists, impeding the reuse and comparison of experimental models. A common form of documentation is the description of the used materials and setups within a publication or report of the investigation. Moreover, the interpretation of these reports requires background knowledge of experimental standards and methodology in the domain of tribology, as the description of the experimental design often contains no explicit stated link of the underlying methods. However, publishing results in reports and publications, as well as the lack of unambiguous routines for dealing with data, impede the access to data. Moreover, isolated and heterogeneous data sources complicate the standardization of results, handling, and data processing. Classical databases, like relational databases, are highly purpose-oriented, thus depending on the format of data, the organizational demands, and potential on-top applications, which consume the data. Thus, dissolving data silos by integration in a central data warehouse is hardly feasible. Therefore, for dealing with heterogeneous and ambiguous sources and the exchange of data between isolated systems, semantic technology and linked data technology have tremendous potential solving standardization and formalization issues. A main difference between semantic technology and, for instance, relational databases is the kind of data handling. While the former deal with the meaning of the data by exploiting ontologies, the latter merely deal with the structure of data and thus are dependent on highly structured, clean input data. Due to the focus of meaning, tabular measurement data can, for instance, be linked to textual result interpretations from publications independent from the source on the format. In this context, ontologies support a machine-machine, human-machine, as well as human-human communication by providing an explicit specification of a conceptualization. Therefore, we came up with an ontology database for the domain of tribology. An ontology defines relevant concepts for a specific domain and the relationship in an explicit and formal as well as human-readable way. Thus enables the formalization of knowledge and the linking of data from different sources for supporting reuse and retrieval within the domain of tribological experiments. We named our newly developed ontology TreeBane, derived from the ancient Greek word tribane, which means rubbing, and the acronym AI, which stands for artificial intelligence. TreeBane is based on reusing concepts from the Ontology of Scientific Experiments, EXPO, which is an intermediate level ontology providing concepts for linking and annotating knowledge gained from experiments independent of the domain. The TreeBane ontology additionally contains domain-specific concepts for formalizing background knowledge into 3 areas: experimental design, experimental procedure, and experimental results. A sample in the TreeBane ontology represents a knowledge carrier which connects information from the 3 areas. Since conclusions in the tribological domain are based on statistical analysis and comparison of measurement series, samples are grouped and compared to groups of reference samples. Every sample group and reference group is represented by a tribological reference method containing structural as well as operational information on the studied samples and experimental design. Since not only the material is In context, define a tribological system. The reference method contains concepts for describing the structure and properties of the tribal system, stress collective, and interactions. For each sample, measurement series are produced as output from a specific device. Due to this, the area of experimental procedure within the TreeBane ontology provides concepts to formally document information about the experiment itself, for example, test setup, device, as well as potential pre-processing of the sample or parts of the sample. Finally, the interpretation of the outcome from testing results in an assertion about friction-aware behavior. The components of TreeBane can be separated in 5 layers. The data source layer consists of the sources containing the data to be linked, for example, CSV, tabular data, natural language publications, relational databases. For every specific source, a mapping scheme or a scrapper has to be created to connect the data sources with knowledge base. The knowledge base itself consists of a triple store in Resource Description Framework, RDF, which distributes data in triple format. This means data is stored in the form of subject, predicate, object, where subject and object do not necessarily have to be from the same source. The TreeBane ontology is used as the global semantic scheme for the knowledge base connecting the relevant concepts and the relationships in the domain of tribological experiments explicitly. Over a SparkQL endpoint, data and information can be retrieved by structured queries. The endpoint can be supplemented by the application layer, which provides a search and retrieval interface or even analysis tools. As mentioned before, assertional knowledge from experiments in the domain of tribology is usually published in natural language. Thus, publications are well-suited knowledge source for acquiring the current state of tribological findings. Dealing with natural language sources is usually problematic since it's ambiguous and unstructured. Moreover, textual descriptions may be incomplete in the sense of formal models. Due to the time-consuming process of acquiring and structuring knowledge from textual sources in semantic literature studies or manual database constructions, those knowledge bases are not suited for long-term reuse and continuous extension. The structured format then allows querying the vast content in a sophisticated way instead of searching articles by keywords or processing the information manually. In terms of the results from tribo experiments, publications similar to Wikipedia contain structured, for example, operational parameters, wear rate, coefficient of friction, and unstructured knowledge, for example, interpretive description and discussion of the results. By extracting the information from text in a structured way, the knowledge can be queried, processed, and compared. Thus, one could query for tribological experiments on desired materials and testing conditions. For example, dry running pin-on-disk model tests with various reinforcement phases within composites or deposited coatings on specimen surfaces. A large-scale employment of aforementioned knowledge extraction approaches, however, strongly demands for strategies for automatically or semi-automatically streamlining data acquisition. For these reasons, we recently came up with a semantic annotation pipeline based upon natural language processing methods in order to overcome the knowledge re-engineering bottleneck and to semi-automatically streamline the knowledge aggregation from publications within the domain of tribology. The inputs for the pipeline are publications of experimental investigations and in particular experiments of the category model test. The output is structured and linked data in form of JSON files, which can be visualized as graphs. The pipeline is built on state-of-the-art language models and NLP techniques. The developed semantic annotation pipeline consists of 3 separate modules and a graphical user interface that can be accessed online. The first module performs the pre-processing step, where plain text as well as elements like figures, charts, or tables are extracted by parsing, segmentation, and aggregation. The document annotation module performs the actual annotation process. Due to the knowledge object generation, different terms used to describe the same entity within a text are aggregated to a single object. The generation of knowledge objects is mainly based on identifying acronyms and synonyms. The document analysis module is a Q&A system that extracts answers from the text to questions about tribal model tests to create triplets from the document. The bidirectional encoder representations from transformer model, or short BERT, is fine-tuned by question-answer pairs. Question templates are generated, which contain the questions for extracting knowledge objects from the text. Those templates determine the structure of the information which should be extracted from the text. The decision maker is an intermediate aggregation step containing multiple redundancies, which ensure higher reliability of an extracted answer. The final result is an ID of a knowledge object and its textual annotation. The output from the document annotation module is a linked data structure containing the aggregated knowledge objects related to dimensions within paragraphs and tables of the publication. Therefore, the output can be visualized as a knowledge graph containing the structured data annotated within the respective publication. This is exemplified on the left-hand side for a representative publication. The generated knowledge graph is a complex network of nodes and relationships. Thereby, the size of the nodes corresponds to the number of mentions of a knowledge object within the publication. The output from the document analysis module, on the other hand, is a graph generated from the question template, which can be seen on the right-hand side of the slide. The knowledge graph contains the identified and correctly classified answers given by the decision maker. Thereby, the tribbles are generated from the scheme provided by the TreeBane ontology. The generated linked data combined with an ontology provides a formally and semantically unambiguous representation which can be queried, filtered, and further processed. This brings me almost to the end of this presentation. To summarize, within the domain of tribology, enterprises and researchers are constantly working on new concepts, materials, lubricants, or surface technologies for a wide range of applications. This is also reflected in the continuously growing number of publications, which in turn serve as guidance and benchmark for researchers and developers. Due to the lack of suited data and knowledge bases, knowledge acquisition and aggregation is still a manual process involving a time-consuming review of literature. Therefore, semantic annotation and natural language processing techniques can decrease this manual effort by providing a semi-automatic support in knowledge acquisition, and this in turn will accelerate and multiply the impact of machine learning and artificial intelligence methods. That shall be all from my side. Many thanks for switching on, and I'm looking forward to a fruitful discussion in the designated Q&A session. Thank you.
Wow, that was amazing, Max. That was a lot of information, and I can see from the chat section you had a lot of admirers, a lot of people that were asking where the source of some of this information was, and I see that a lot of it is in some of the publications that you've I think put out. I would encourage everyone to hook up with Max during. You can link together during the conference here, and you can have private chats if you have further questions about it. I do have one question. Is this material, is that part of one of the classes that you teach, or is machine learning and tribology an actual class that you teach?
So far not. I'd say it is rather a research direction that has recently really initiated. So it's still quite a young field in the domain of tribology, because I think there have been a lot of doubts around, especially for the application of machine learning, especially in the domain of tribology, because of all the points mentioned. That is a very interdisciplinary field. We have very many influencing factors. If we confer or conduct an experiment in one lab with one equipment, we get one result, and we will get something slightly different when we conduct it in another laboratory. So we're not speaking about hard data, and the challenge is that every measurements we do, we're trying to figure out loss variables. We cannot repeat exactly the same measurements, because the friction, the wear, these are loss variables and no hard data. So we're still, I'd say, in the first steps of really applying machine learning in the domain of tribology. So far, this is not really entered state of the art and yeah, classes or lectures, but of course we're working on this topic together with a lot of students, rather in the form of thesis or projects than really teaching the theory in classes. Of course, there's the theory of tribology, or the domain of tribology, that we did teach, and also machine learning approaches. But to marry these two fields still is quite a challenge.
Yeah. Well, I appreciate you taking the time today. Everybody has about 5 minutes to get to their next session. Max, thank you again for your help. I would encourage everyone again to link up with Max through the LRVS app and pick his brain a little bit more if you need to. Thank you, Max.
Yeah, thanks a lot. Thanks for having me.
You bet. Bye-bye.